Hello, everyone, and welcome to another lecture for Auto 105 Manual Powertrains. Today, we're talking about Chapter 12, which is the theory and operation of a manual transmission. So, we're kind of jumping ahead where we left off in the textbook. We're jumping into transmission systems because we talked about clutch systems. So, it kind of makes a little bit more sense to go in order of how the powertrain is laid out in the vehicle. So, we've already have a firm understanding of how our clutch is going to decouple and couple our engine and transmission together. Now let's talk about the construction of the transmission itself. For what we're going to talk about today is we're going to talk about manual transmissions that are meant for front engine rear wheel drive. And we will have a separate lecture talking about transaxles. The big difference between the two is our transaxle is going to have an integrated differential to where our transmission does not. There will also be a couple other construction differences too, to where our transmission for our rear wheel drive application is going to have three shafts: an input shaft, a output shaft, and a counter shaft, where our transaxle will only have two shafts. So a couple things to keep in mind right there. Our transmission, though, when we look at what transmission is going to be in what vehicle and why it's in that vehicle and why it's used for, we have to make sure that we have an understanding that it can handle the torque of which our transmission is going to be delivered by the engine. Now, the size of the transmission is often kind of not always fully understood. When we talk about size of transmission, we're actually talking about the separation between the two shafts, between our input shaft and our counter shaft. The larger the spread between those two, the stronger the transmission will be, or the more torque it can handle. It is going to be important, though, that we do have an understanding of how all of the components in this work, because we can have a transmission that might be considered somewhat weaker, be able to handle more output torque based off of how the vehicle's driven and how it's operated. Now, when we look at how we're rating transmissions, we're rating transmissions based off of their torque output and its capability, and that's going to kind of correspond to what type of engine it has in it. An engine, for instance, that's a little bit older might not have as much output torque to where a modern engine that's going to be rated for its maximum torque output will be, a little bit more fine tuned on what we're going to have and what we're going to see and what's going to go through that gearbox. Prime example of that is I have two gearboxes here photoed for Corvettes. Our first one on the right there for number A, that's from a C2 Corvette, and it's a four-speed. Now, it's a four-speed in the understanding that we weren't going cruising on the highway with the Corvette, so we only needed four forward gears that were first through third were underdriven, with fourth gear being direct drive. But if we look to a 2018 Corvette, we're looking at that being a seven-speed manual. Probably going to have three or four underdrive, one direct drive, and then the remainder of those gears being overdriven gears so that we can cruise, because we're more likely to cruise on the freeway with a modern car. And vehicle speeds have gone up quite a bit. But if we also look at the output torque between those two Corvettes, we're probably triple the output torque that we once were, if not quadrupled. It is important to remember that a lot of these old classic engines, although they might be big and they might sound loud and might have a horsepower that seems high, the way that they rated horsepower was not the most honest. It also too was they weren't huge on torque because we had to move a lot of rotational mass. So we are getting into where a lot of cars are revving a lot higher. They have a lot higher output torque, and thus the transmission has to be able to withstand that. However many gears the transmission does have, we're going to be multiplying torque, or we're going to be multiplying speed based off of what gear. First gear is always going to be the lowest ratio, or give us the most torque multiplication, with our high gear, in the case of that four-speed transmission, fourth gear in the case of that seven-speed transmission, seventh gear being the highest gear or giving us our most speed multiplication. When the driver shifts through each gear, they're shifting sequentially through each gear. They're going first, second, third, fourth, fifth, sixth, and then possibly seventh, if that's the case. And they're going through each gear in a manner that we are increasing the vehicle's forward velocity and decreasing the output torque going to the drive wheels. We'll have more torque in first gear than we'll need in fourth gear because the vehicle's already, started moving from a stop. There's built up momentum, and we just have to maintain that momentum as the vehicle goes forward. When the driver shifts into each gear, we do have to decouple the engine and transmission. So that's where they're going to press the clutch pedal. As they press the clutch pedal down, they're going to take the shifter, put the shifter into neutral. That's a key thing that a lot of people forget, is that oftentimes people just try to shove it into gear. You got to have it in neutral, and then you put it into the next gear. So if you're in first gear, clutch all the way in, neutral, second gear, clutch back out. Not, clutch going in and you're trying to shift at the exact same time. Now, a skilled driver can do it relatively quickly, but we need to make sure we're slowing down and engaging it as need be. I brought up at the very beginning that we have different shafts inside of the transmission. Our rear wheel drive transmissions are going to have three shafts: the input shaft, main or output shaft, because it can be two names, and our counter shaft. And it will be different in construction than our front wheel drive transmission. Now, you will be tested on this, so you will see this again. So do keep that in mind. Oftentimes, repair manuals can talk about shifter linkage being a shaft. I'm talking about what shafts the speed gears are located on. In that case, some of our gears will be fixed to the transmission itself. In other cases, the gear will be movable. So let's look at that really quick. I'm going to go back and forth between a transmission cutaway that I have. Now, if we look at my cutaway right here, so my input shaft has this counter gear that goes down to my counter shaft. The counter shaft is an as-cast shaft. So my counter shaft, my second gear, first gear, and reverse are all cast. These are all of our inputs. So power transfers from here down through this shaft, and then whatever either this second gear, third gear synchro, or first speed gear, whichever one of those is locked into place, will engage to the output shaft. And the output shaft starts right here and goes out our tail shaft. And tail shaft, you can see that would go out to the drive shaft of the vehicle. Our second gear, speed gear, and my first gear, speed gear, these are free spinning from the counter gear, and they are separate. So we can either have it to where it is an as-cast gear or a separate gear. And the speed gears, like I have this separate speed gear from a Subaru BRZ. This is what a speed gear would look like, and that would ride on one of the shafts. The shafts will have splines and or bearing riding surfaces depending on what type of gear or what type of component is being slid onto it. And oftentimes we're going to have snap rings that are going to retain these components. Now the snap rings can be there as a stop or as a final resting spot, and they're being interference fit. So when we go into the shop and start rebuilding these transmissions, we are going to be doing so with the shop press and pressing stuff apart. Now we can have grooves cut into our shafts themselves for lubrication and to lock everything in, and then our bearing surfaces are going to be smooth. That speed gear that I just showed you that was separate from the Subaru BRZ, that would have a Torrington or a needle bearing inside of it that would allow for smooth operation so we can reduce friction. We're trying to reduce as much friction as we possibly can inside of a manual transmission because we are going to have these gears in constant mesh. Now, I will show you with our 3-speed when I do start talking about how it's going to shift. I use it as a good example as a cutaway because we have one set of gears, second and third, synchronized, and then first and reverse as non-synchronized, or actually a gear clash style. But all of the gears will be in constant mesh, meaning there's going to be a lot of friction and a lot of load on everything. So we will have the speed gears spinning on non-friction bearings. When we look at lubrication too, inside of these manual transmissions and transaxles, they are going to be what's called splash lubricated. And I'll get more into that a couple later slides, but effectively there's no pump and it's only being lubricated by the fluid that's being flung around in there. Now we have a couple different type of bearings that can be inside of a transmission. We can have tapered roller bearings, ball bearings, and then those needle bearings like I brought up in those speed bearing, speed gears, excuse me. There also is some transmissions that we don't have bearings at all, but instead we'll have a bronze bushing or a softer material that acts as a bearing material. Either way, whatever type of bearing you do have, we need to then take into consideration what that bearing needs. For instance, a tapered roller bearing, for instance, will need preloads, where a roller bearing or a straight, ball bearing will not. Now, quite often we can have uncaged bearings as well, and those will be located in the end of the input shaft, which we'll see here in a second. Now, we talk about our input shaft. Our input shaft is the simplest of the three shafts of the transmission. It is going to be poking out external of the case, and it will have the clutch disc splined to it. It will also have typically a pilot bushing on the end to ride in the back of the crankshaft or the flywheel to allow for it to be supported. The one thing that the input shaft has a lack of is it does usually have a lack of support. Inside of the case, it's going to be supported by what's called the pocket bearing, and the pocket bearing lives inside of the shaft, and that can be that straight roller bearing that's uncaged. We'll usually have one input gear or counter transfer gear as cast to it, as well as we will have the synchro meshing area for fourth gear. Now that's going to be key because fourth gear or whatever our direct drive gear, in the case of my cutaway transmission, it will be third gear, is going to be direct drive. So there's going to be no torque multiplication and no speed multiplication at that point. Now our pocket gear or pocket bearing, excuse me, the pocket bearing, this is where it's living inside of the input shaft. This is probably by far the most important bearing for the transmission, and we do not want it to fail whatsoever. If this does fail, it tends to cause the input shaft, the output shaft, and the counter shaft to all wear on each other, and that does wear the transmission out to where nothing's rebuildable at that point. But this is a non-caged bearing. They're typically straight roller bearings, or they can be a series of straight roller bearings. In some cases, you can have two sets of them. That's more for the counter shaft, though, typically. And it will ride on a hardened bearing surface on the end of the output shaft and or main shaft. That's what the manufacturer is calling it. The transfer gear will be a helical gut gear, again, for quiet operation. And we will see that on most of the gears in the transmission. The only time we will have an exception to that is in reverse on some transmissions, and that's because it will not be synchronized. It will actually have a gear that comes up into place. Now, I did bring up that we will have the synchro locking ring for fourth gear or whatever gear happens to be direct. And we also have a good view of that as well right here. So my pocket bearing being in the middle, we have those rollers, but I have my synchro sleeve right here, and then the dog teeth right here that are going to lock into the blocker ring or Bach ring, depending on the manufacturer. And that locks in that direct drive for typically it's fourth gear, and the example I'm going to give you is third gear. However, I do want to make very clear that my 1952 Ford transmission is not an atypical transmission, not at least now anymore. But it's really light and easy, and it shows a multitude of different ways that we can shift gears. That's why I have it as a cutaway. Our main shaft is going to be also known as the output shaft. It will have speed gears attached to it. The speed gears are what's going to be locked to that main shaft. And as they're driven by the counter shaft, which is going to be our input, that will give us our gear ratio change. Either a low ratio, like first, second, or third, or a high ratio, like fifth and sixth, to give us overdrive. In some cases, transmissions will be synchronized. That is where we're going to have a device that is going to allow for smooth operation and allow the output shaft / main shaft to get to the same speed of our counter shaft. The synchronizer hub itself will be pressed onto the output / main shaft. And the reason being is it has to be locked to the shaft. So those splined areas are where it's going to be locked to. And that will allow for when the synchronizer locks the speed gear in place, we can transfer that torque to the output shaft and then down to the wheels. So what we'll see here on this shaft that has everything removed, this is going to be our main shaft / output shaft. In the very front there, we'll have our pocket bearing journal that will go and nestle inside of the input shaft. From there, we'll have the different synchronizer locking splines. So we'll see the third, fourth locking splines on the front there. That again will usually be held in with a snap ring as well as an interference fit. We'll then move on to the third gear speed gear journal. And then we'll also have the speed gear journals for first and second, and then the lock for fifth synchro as well. Why we're doing that is, again, we're having the speed gears be free spinning, and we're going to be locking the the synchros to the shaft so that we can transfer the power out. At the very end there, we can see the drive shaft splans. That's going to be very indicative of a slip yoke transmission, or a transmission that will have a drive line that will slide in and out of the shaft itself to seal itself. Now, our main shaft, those polished journals are going to be for those frictionless bearings and or our bushings to ride on, and that's going to be an area that we do need to check for wear. And we should have the speed gears be able to spin freely on them when the shaft is out. When the transmission's fully assembled, the speed gears will be in constant mesh with the counter shaft, and so therefore they won't be able to spin freely because the counter shaft will be spinning them. But when the transmission is in neutral, for instance, and the clutch released, the input gear will be going down and spinning the counter shaft, but because none of the speed gears are locked to it, it will just be free spinning and sending lubrication up to the top of the transmission. Now, our counter shaft, or the lower shaft in the transmission, our input and our output shaft, they're both on the same plane. Our counter shaft is right below it. The counter shaft typically is going to have all of the gears as cast to it. So it's just one giant casting with multiple input gears that go along with it. These multiple input gears will change in diameter based off of what gear is being selected. So, for instance, if we're looking at first gear's input is going, since it's the lowest gear ratio, we'll have the smallest diameter and smallest tooth count. To our output, will on the main shaft slash output shaft, we'll have the largest tooth count and the largest diameter, kind of going back to chapter 3. We will have bearing journals on either end. We can either have the counter shaft to where it will have bearings pressed on it, and the shaft will be load supporting itself, or we can have the gear cluster that can be separate from the actual shaft, and the shaft have a set of roller bearings, and that's where you'll see those double decker non caged roller bearings in a lot of cases. This component too, when we look at actually overhauling a transmission, can be the most expensive depending on the transmission design. This is especially the case on transaxles. The counter shaft on those can be extremely expensive. Now our reverse gear. Now our reverse gear, we have to have the ability for the vehicle to back up. Our reverse gear tends to be straight cut gear and not constant mesh. So we can see with the mechanic here taking apart our 5-speed, we have a set of spur gears, and the reverse gear at the top there that's closest to the mechanic's left hand would be moved into position. I have an example of that here on my 3-speed. First gear is a non-synchronized gear, and you're actually moving it into place. It will ride on its own shaft with its own set of trundle bearings to support it, but we're not including that as a shaft because it's a little bit separate. In some cases, the reverse gear can be a part of the synchronizer hub for first second, which we will have on the S40 Honda transmissions that you're going to be taking apart. But more atypically, we're going to have the reverse slider being separate, and that being a very low ratio. Now, the important thing to understand with a reverse gear is all of our forward gears, it's going to be one input to one output. But reverse, we will not. Reverse, we want to remember that we're going to have an input, an idler, and an output. So it'll be a set of 3 gears. So on the photo there on the right of the screen, we can see I have my input at the very bottom with that large nut. So if I draw on it, this is going to be my input. This one's going to be my output. This one's going to be my idle gear. And the idle gear, again, is just there to allow for the gears to change directions. Because anytime we have 2 gears meshing with each other, if our input is rotating clockwise, the output's going to rotate counterclockwise. So with the idler gear, the input will rotate the idler gear So if the input's rotating clockwise, it rotates the idler gear counterclockwise. The idler gear rotates the output counterclock or back to clockwise again because it's rotating counterclockwise. Therefore, we have the change in direction that we need to get the vehicle to go into reverse. Our speed gear is going to have a couple different things featured in it as cast. Our first area that we're going to be looking at with our speed gear is this section right here, which is our constant mesh set of teeth that will be in constant mesh with the counter shaft. This will be where we get our gear ratio change. Now, it will always be in mesh with the counter shaft and will always be rotating with it. It's just whether or not it gets locked into place, in which we have the synchro apply that will be locked to the output shaft. The next thing that we're going to have is we're going to have the synchronizer application hub or the slide right here. This is where the blocker ring is going to start to grip to get the speed gear to the same speed as our counter shaft and then slowly bring it into the same speed as our output. And then the very second component or third component we'll have is going to be the dog teeth, which are these little pointed areas on the end of the speed gear. So all three of these different sections we're looking for wear and damage if the transmission does fail, and all three of these sections have unique characteristics that allow the transmission to operate. The teeth are in constant mesh with the counter shaft, and that's where we're getting our gear ratio change. Our synchronizer sliding hub, that's going to allow the synchronizer to start to bring the speed gear and the output shaft to the same RPM as the counter shaft. And then our dog teeth are going to lock the synchronizer slider, blocker ring to the hub, and that will then lock everything in and keep it in gear at that point. I brought up that these components are going to be splash lubricated, and splash lubrication is going to be where the counter shaft is going to go through the oil and then fling it up on top of our speed gears, and they're just going to be kind of gravity lubricated. So whatever oil gets up on top of it, it's what's lubricating it. There can be channels. So in the case of our S40 transaxle, it does have kind of a channel ducting kind of system that allows for gear oil to be directed once it's flung up and fallen into its trough, be directed to different components, and it can spill out onto some of the speed gears. But the bearings that are inside of this need to be frictionless because they're expecting to not really run with a ton of lubrication, not at least pressurized lubrication. It's a non-pressurized system inside of there. Now, all of those three shafts will be housed in our normal transmission case. And then on top of the transmission case, depending on what kind of output we have, if it's a four-wheel drive or a rear-wheel drive, we will have a different type of extension housing. This is going to be the rear section of our transmission case, and it will always be removable. And it's removable because most manufacturers are going to design a transmission for a particular model vehicle that can have different drivetrain layouts. So what they'll do is they'll be able to keep the exact same gearbox, but then swap out the tail shaft or the extension housing to make it a two-wheel drive or to make it a four-wheel drive transmission, if that's the case. With this application here, we have a speedometer drive that's out on the output of this, and the speedometer drive will have its own set of gears. But inside of this extension housing, there's going to be a couple bearings, and it will just support the output shaft, and it can have a seal that will accommodate for the slip yoke. The other part of the housing that we're going to have that's external is going to be the bearing support. In particular, this is the throwout bearing support up front. So this will go over our input shaft, and we can start to see the splines of the input shaft there on the photo on the right. And we will have this area that is smoothly machined over the input shaft for the throwout bearing to ride. So that when we press the clutch pedal, the throwout bearing is then pressed against the pressure plate's diaphragm springs, and we can release the clutch. And then it has a smooth transition back. Why these are important is oftentimes we have to remove these to gain access to an input shaft to free up the input shaft itself. That snap ring will retain it under there, as well as there will be a lubrication channel. We can see in the casting right here, this little area right here is going to be a lubrication channel that it's going to be splash lubricated and send fluid to the front bearing that the input shaft can have right there. All right, now let's talk about the synchronizers themselves. Now they can be called bulk ring or they can be called blocker ring. It really kind of depends on the manufacturer. It's ultimately the same thing. We're just kind of getting into the nuances of the vernaculars with automotive components. What this will allow for is this allows for smooth transition from each individual gear. Before we had synchronizers, we would have crash box transmissions or transmissions that slid the gears in place, and we would have to double clutch to be able to get smooth, non, damaging to the transmission engagement. So what that meant was that meant you would put the clutch pedal in, you would take the vehicle out of gear, you would release the clutch pedal, and what that would do is get the output shaft spinning at the same as the wheels are spinning because it'd be connected to it via the drive shaft. You put the clutch pedal in again, and then you'd select the gear. You'd have to select the gear in a manner that you were doing it smoothly to where you weren't causing any damage. The transmission that I'm going to show you as a cutaway is an example of that. And we have a first gear and reverse are a slid gear design. Obviously, that required a lot of talent to be able to shift in and out of gears smoothly without doing any damage, as well as it was not very efficient. So we started to come up with these synchronizers that allowed for the constant mesh speed gears and allowed for smooth operation with one clutch engagement, disengagement. Now we're going to have several different components that make up our synchronizer. We're going to have our slider, our hub, our blocker rings or bulk rings, and then the speed gears themselves. The rings, the blocker rings themselves or bulk rings are typically going to be made of bronze or brass. They're going to be a little bit softer material. And when you hear people saying that a transmission, a manual transmission in particular, has to be overhauled, this is the wear item that gets replaced, is just these little blocker rings. We're going to have an inner conical section that's going to grip against the speed gear as they get engaged. So the hub, which is the central portion of our synchronizer, is going to be attached directly to the input shaft and is usually retained with an interference fit and snap rings. And we don't want this to come loose, and it will have inner splines. So that orange middle section, the clutch hub, is going to be locked to the output shaft, and it will not turn unless it's locked with the speed gear that's being driven by the counter gear. The next components we're going to have is the synchronizer sleeve, which is in green on the left there. And that synchronizer sleeve is going to be moved, and it has a collar that goes over it that will actually allow it to move and just get moved by the shifter. That then will lock into place via a set of splines onto the synchro rings or the blocker rings. And we're going to have one for each speed gear. So in the diagram that I have photoed here, if you go to the far left, you'll see just one synchronizer ring, and that's because the speed gear is out of frame. But if we go to the right, we have the key springs or the detent springs that prevent the synchronizer sleeve from coming undone or slipping off and popping out of gear and locking onto our synchronizer ring. And then the speed gear itself will have the cone that is counter machined to allow for it to lock into place. Now, the blocker rings are going to have two styles of construction. Again, they're always going to be made of a softer bronze material for the dog teeth, but we can either have what we have for A, which is going to be finely grooved machined surfaces that's going to grip the cone for the speed gear and will be a using gear oil, or it will be a paper material or a friction material that's bonded to the inside of it, like what we have for B or the lower photo. And that's going to be a paper-based material that will be bonded to the synchro ring, and both are serving the same function. They're both going to be locking the blocker ring to the speed gear to bring the speed gear and output shaft to the same speed of our counter shaft. The difference, though, is our friction material that's paper or bonded to it will be using automatic transmission fluid. We're going to be using much thinner material. The friction material that we'll see on these type of blocker rings will be the same friction lining, paper-based lining that we'll have in automatic transmissions. Now, our little dog teeth that are on the speed gear and that are on the blocker rings, Those can be moved, and they're not always in the same relation as themselves, and they can be moved from one side to the other as the transmission is in neutral. But when we select a gear, the synchronizer sleeve is going to start to lock the teeth in on the blocker ring, which is going to correspond with the cone that it has on the speed gear to wedge it into place. The chamfer of those teeth are going to allow for everything to center up. So we can see that there's a chamfer on the teeth that allows for everything to center and lock in place. So if we look at this diagram on engagement, we can see on A up here on our far left corner, so this is going to be our first step, we're going to be moving the sleeve via the shifter against the shifter sleeve that's going to start to engage on our second engagement here for B into the blocker ring. Now, the blocker ring is going to then wedge the conical section for section 3 here, so this area right here, against the speed gear to start to bring it into the same rotation. And as it starts to build rotation, then the second set of teeth for our fourth action right here get locked into the slider. So because our slider is locked to not only these teeth, the blocker ring teeth, but also our hub teeth, all of the torque will then be transferred out to the output shaft from this point. Now let's look at that in operation on my transmission cutaway here. So my second and third gear here is synchronized. When I shift it backwards, I'm shifting into second gear. We'll have a better visualization of the blocker ring and third gear right here. So we can see with it in second gear, the blocker ring is free to rotate, and it can rotate independently of the speed gear and of the hub itself and the slider. But as I engage the slider, right, so we have second gear's blocker ring right here, the teeth will line up. So even if I get them misaligned, so we'll go misalignment like that. If I shift slowly into second, you can see everything start to line up. And when I move everything, everything's in line. What that's doing is the tapered on these little tapered corners on these dog teeth, and I apologize, camera's a little bit blurry, but it's getting lined up with our slider assembly and it's locking everything in place. As it stands right now, if I hold my output gear, the transmission would be in neutral. Now, when I lock it into second gear, I now can't hold it. Power is transferring from my input down to my counter shaft because the counter shaft is in constant mesh with my second gear right here. It is going to be always turning this, but what I've done is I've locked it with my synchronizer, and that is locked the speed gear to our output shaft, and that's going out and driving our drive shaft at this point. And then when I shift into third, it's just as smooth. Now, second gear, it's going down through this set. Third gear, though, however, when I shift into third gear, this is locking the input shaft to the output shaft. So we're going straight through with our torque output. This would be fourth gear on a modern transmission. To kind of get a sense of that, to see the components individually, if I have my Subaru synchronizer right here, I can separate the hub and the slider. I can separate the blocker ring. Now, inside of the blocker ring, I have those little fine metal grooves, and this is a full brass synchronizer sleeve, and that is going to act against this cone. So as the slider, because the hub is missing, this can move freely, but as I put pressure on it, it locks it into the gear, and I can't spin it independently. And that's because these little grooves grip onto this cone right here. And that starts to get this gear and the hub start to spin at the same speed to where these teeth get locked into the slider's teeth as this slides over. So the slider is going to be partially engaged on the hub, but primarily engaged on our dog teeth for the speed gear and for the blocker ring right here. Now, in some cases, we won't always have the dog teeth attached to the speed gear. Instead, we'll have them separate, and this will be a pressed-in fit. This will be on transmissions that will have either they can have two-ring synchros, or they can have the ability to change out the speed gearing very easily. Now, I did bring up that this is the more modern method is our synchronize, and this transmission is got a mix of both. So our first gear is up here, and when I'm shifting it into first gear, I'm actually physically moving the gear in place. And this is how transmissions shifted before synchronizers. So with it in neutral, the output shaft isn't turning. When I shift it into first gear, I'm physically moving this gear into place, and now my output is being allowed to turn. And I'm going down through the counter shaft through my smallest gear that's cast on here, and then up to the output. Now, with it in first gear, you can just start to see the idler back here for reverse. So if I shift it into reverse, I've now engaged the idler. If we look, these gears aren't actually touching. I can get my pocket screwdriver in between the teeth. And that is because our input shaft is driving the idler, and the idler is driving this output gear or speed gear for first gear. When we're shifting into first gear on this particular transmission, because we're stationary, we don't have to double clutch. One clutch engagement is going to be fine for this. But if we were to try to downshift, if we're in second gear, for instance, and we're trying to downshift into first, that would then mean we would have to double clutch this particular transmission. And early transmissions are going to be of this design. So this is kind of a unique transmission, and that we have both coming out of our input shaft right here. But that's neutral. So we go first gear. The shift linkage, when we go to shift to second gear, pops this out, pops that to second gear, third gear, and then if we wanted reverse, we're going into reverse that way. So this transmission technically has 4 speeds. We have 3 forward and 1 reverse. Now, the selection of the gears for the transmission will be done through the gear selector. That can be located on the column. So my old 64 Ford, it was on the column. But more often than not, it's going to be on the floor. And it will be shifted by, if we're a left-hand drive car, by your right hand. If it's a right-hand drive car, your left hand. But the gear pattern will be the same for both in terms of where first gear is and where second gear is. It's just whether or not it's away from you or towards you. We can have the shifter directly attached to the top of the transmission, like we have here for our T5 transmission that's photoed on screen. The shifter is directly attached to it, or it can be via linkage. The Honda S40 transmission that we're going to be rebuilding, that will be via linkage. It will have a shift bar. The transmission that I have on the bench right here, the 1952 transmission, it was a call-in shift, and it had its linkage attached to the side of the case of the housing. Either way, both methods are going to be attaching to either whether it's on top of the transmission or whether or not it's via linkage, will be attached to a set of collars that are going to go over our sleeves. Now, these collars are going to some of the time they can have bushings or bearing services. In the case of this older Ford transmission I have right here, they're just as cast or cast iron. The cast iron against cast iron is usually just fine. But these U-shaped collars can have wear pads on them that do need to be inspected and require replacing. The shift collars or shift forks, they're going to be paired to gears. So as we saw in that older transmission, first and reverse were paired, and then second and third were paired together. And that might be different based off of each individual transmission on how they're pairing and how they work. This being a 3-speed transmission, there only being 4 gears, we can only have 4 pairs. And it makes sense to have first and reverse and then second and third paired together. But we will almost always have a first, second synchro, third, fourth synchro, and then sometimes a fifth reverse synchro. The textbook, when we go into the next chapter, it goes in overhauling a transmission, and it's a T5 transmission, which is a very typical 5-speed design transmission with 3 underdrive ratios, 1 direct drive, and 1 overdriven ratio. And the synchro layout is going to be the same for a lot of transmissions. The S40 transmissions we're rebuilding in class, those are also 5-speed transmissions, and they go off of the same shift strategy for the gear selection. Now, our gear selectors are going to have little detent rollers in them. Now, these detent rollers in them hold the transmission in gear. We also have the springs inside of the synchronizer to prevent the transmission from popping out of gear. Those of you that have ever experienced a transmission that pops out of gear, it's not a lot of fun because it tends to pop out of gear after you've shifted and you're just beginning to move your hand away, and then the shifter goes and hits your hand. And especially if it's a low range transmission. So like for instance, there's a TSB and a recall for older Jeeps that do that. It hurts real bad when it pops out of gear because it pops your hand, and because there's a lot of output torque because it's in first, it really whacks you. But they will be held in place with these little roller detents. Now these roller detents will also act as an interlock method so that you cannot shift into another gear. They're going to be a little roller bearing that once you are in neutral, you can roll over one channel or another. But once you've rolled over the channel and the roller bearing is driven into the other shift rods, it locks them in place and it prevents them from being shifted. So, the people that say that they shifted a vehicle from fifth gear to reverse on the freeway, to do that, they either have used so much force on the shifter that they would have damaged the transmission regardless, or they've tampered with it. Mythbusters tried doing it, and they actually had to take the transmission apart, disable these detents to be able to do that first into reverse type situation, or that fifth into reverse while you're at freeway speed, for example. But it is possible you can, manhandle it in if that's the case. In some cases on modern transmissions, we will have a reverse lockout solenoid that will prevent that. And again, that's preventing the driver from accidentally shifting into reverse and causing catastrophic damage to the transmission, powertrain, and drivetrain components. And this will be PCM controlled. And it will be looking for the vehicle speed to be below a certain threshold and for the clutch to be fully engaged and the shifter to be selected correctly. In some cases, we can have paddle shift. Now, if it's a paddle shift transmission, like what I have folded here, it will either be an automatic transmission that will have the ability to be a manual valve body when selected, or this will be attached to an electronic control unit that will then move solenoids on the side of the transmission case to allow for you to shift and to shift quickly. So these paddles they'll be usually a plus and a negative, and it will be based off of where the manufacturer puts them, and they will allow for the driver to be able to shift via just hitting the panels on the steering wheel. So we've talked about kind of the components of the transmission. Let's talk about how the transmission is going to operate and what each gear is going to look at. I kind of went over that when I looked at the Cutaway going through that transmission, but we'll look at a more modern transmission, how we're going to be selecting each gear and then what it's going to take in terms of gear ratios that we're going to see. Now, all of this, again, is going to rely on the driver to depress the clutch pedal to disconnect the engine from the input shaft of the transmission and allow for smooth transition of the shift. Can you do clutchless shifts? Yes, you can. Is it a good idea? No. Usually it can do damage to the engine as well as the transmission itself. Unless you're super silky smooth, I do not recommend it. Now, in terms of power flow through the transmission, first and reverse will be our lowest gear ratios because that will be moving the vehicle when the vehicle is stationary and not moving at all. So we're going to have to move the full mass of the vehicle and get it up to speed. So those will be our lowest ratio. Now, it's important to remember that our low ratio means a high number. So a low ratio would be like a 4-to-1, with a higher ratio being like a 1.5-to-1. So again, it's opposite in terms of the number is really large for a low ratio, and for a high ratio, the number is really small. Fourth gear tends to be our direct drive. We usually only have direct drive on transmissions and not transaxles. Because a transaxle is a two-shaft transmission, we will not have the ability to lock the shafts together. Now, it will have a near enough to direct drive to where it doesn't matter, but it can give a little bit of advantage if it is more underdriven versus overdriven, dependent on the transmission design. But let's shift through a 5-speed transmission through each gear. So in first gear, our lowest gear ratio, our input shaft will be sending engine torque down through our counter shaft. Because our first gear synchronizer has been slid by the driver via the shifter that's going over the shift fork, that has that collar that's going over the sleeve that has engaged the blocker ring and has locked the speed gear to our output shaft, we're having our lowest ratio. We can see that we have a small gear driving a large gear, so that will give us our lower ratio. Somewhere, an average vehicle, it's going to be anywhere between 3.5 to 4.5 to 1 in terms of our first gear. When we shift to second gear, we're going to disengage first gear by moving the slider away from first gear, which allows first gear speed gear to now free spool on the output shaft. And then that synchronizer blocker ring will start to lock second gear into place against the output shaft. And again, torque from the engine is going to go from the input shaft into the counter shaft into our second gear speed gear, which is now slightly larger in diameter than our input for first, and then our output for second gear is slightly smaller in diameter. It's larger in diameter, excuse me, for our input, and our output will be slightly smaller in diameter. That will then lock into place, and we will go into second gear. Now, second gear will still be a low gear. It will be an underdriven ratio, but it will not be as low as first. So first was, we'll say 3.5 to 1. Second, it might be a 3 to 1, or it might be a 2 3/4 to 1. We're not going to have as low range of a ratio because we've started to build up the momentum of the vehicle and it's starting to drive down the road. However, we are not going to have a higher ratio because we still need to have that torque multiplication to get the vehicle up to speed. From here, when we shift into third gear is going to kick the second gear synchro into neutral, or neutral position, to where neither blocker ring is locking the speed gears. That disengages the second gear speed gear from the output shaft, and now the third gear hub and slider has locked into place with that blocker ring to lock the third gear speed gear into the output shaft. Again, just like first and second, the input shaft is going to be moving the counter shaft. We're going to have a little bit less torque being multiplied at this point because our input gear will be a larger diameter than that of second gear, which was a larger diameter than first gear, and our output will be a smaller diameter than second gear and a smaller diameter than first gear. So if we have, the ratio of 3.5 for first gear and 2.75 for second gear, third gear may be anywhere between 1 3/4 or 1.5 to 1. Again, we're still multiplying torque because we can still accelerate in third gear, but the vehicle has now come up to speed and we don't have to move as much as that momentum. Then when we shift into fourth gear, we disengage third gear from the main shaft, which it allows to free spin. And instead of going from the input shaft to the counter shaft and then back up through a speed gear that's locked to the output shaft, we instead are just locking the input shaft to the output shaft. So in a way, there isn't a fourth gear. There is not a constant mesh gear, nor is there a gear ratio. We, in turn, are just locking the transmission to the engine. So the best way to look at this is fourth gear, or whatever gear direct drive happens to be, is just bypassing the transmission. It's going right through it. And there's no torque multiplication, nor is there any speed multiplication. So first through third, we're underdriven ratios where there will be a torque multiplication. We will have higher output torque than there is input torque, and that results in a smaller input gear driving a larger output gear. For direct drive, it's 1 to 1. So we have the same diameter versus the same diameter. In the sense of this, we don't have any diameter because we're just locking the shafts together. But if we go to fifth gear, which is going to be our overdriven ratio, fifth gear, we're going to disengage the fourth gear synchronizer and we're going to engage the fifth gear synchronizer. Now, this design transmission is very similar to that of our S40 transmission, and that fifth gear will only have a synchro or a one-sided synchronizer. There will not be another one on the other side. So very similar to our underdriven ratios, the input shaft will be sending the engine's torque down to the counter shaft to a very large diameter input that will be driving a smaller diameter output. Now we'll also notice too on this design that in this particular transmission that the fifth gear synchronizer is actually on the counter shaft and not on the output shaft of the transmission, which can be unique in some situations, but isn't unheard of. It's important to remember that we're not doing any torque multiplication in overdrive ratio, such as what we have photoed here for fifth gear. Instead, what we're having is we're having speed multiplication. So we're reducing the input RPM of the engine to increase fuel economy, but we are not multiplying torque. So a fifth gear or an overdriven ratio would be something like 0.68 to 1 gear ratio. So if we have 100 foot-pounds of torque going in from the engine, we're only getting 68 foot-pounds of torque going out to the drive wheels. Because at this point in fifth gear, we've already gone accelerated, we're at our cruising speed, and all we need to do is just maintain that forward velocity of the vehicle. Now, if we were to downshift, we would downshift in a reverse sequence of how we upshifted. So you'd go fifth to fourth to third to second to first. Once we come to a stop, then you can shift into reverse gear. Now, reverse gear on this particular transmission that we have as a cutaway is not synchronized, meaning that none of the three synchronizers that we're going to be using will be used to bring the shafts up to speed. It will be a straight cut or a spur cut design, meaning that we have to have the vehicle stationary to be able to smoothly shift into first or reverse gear. So reverse gear will be a low range gear, very similar to what we have in first gear. The ratios are usually pretty similar to where, if first gear is 3.5 to 1, reverse will be the same or slightly lower, depending on the vehicle, and that's to account for having enough torque if you're backing up a steep driveway. But very similar to our underdriven and overdriven ratios, forward. In reverse, it's the same, except for as it goes down through the counter, from the input shaft to the counter shaft is going to rotate that idler gear, and that idler gear is down below. That idler gear, and it's not very, well photoed here or diagrammed here, will then lock into our input gear that will go out to the drive wheels and reverse the rotation that we have the transmission operating at. Now, a keen-eyed viewer will say, well, the input, if it's turning clockwise, that will be turning the countershaft counterclockwise, and that will be turning the speed gear clockwise again. Well, that's the thing, is we're going to have basically four different rotations when we add the idler gear in. We're going to be going from clockwise on our input shaft, counterclockwise on our counter, back to clockwise on our idler, and then back to counterclockwise on our reverse. So it is, again, a little bit interesting how that is all playing out. All right, let's look at diagnosing some transmission concerns. We're going to kind of fall into a couple different things in terms of what can go wrong inside of our manual transmission. We can have noises, and noises can then lead to shifting issues. And then the second one would be a shifting issue. More often than not, though, they will correspond with each other. That if there is a shifting issue, there's going to be a noise that is corresponding to it. The transmission, again, we don't have a ton of components inside of our manual transmission, but when they do fail, they tend to fail with making noise and being pretty clattery. Oftentimes, the transmission will tell you if there's an issue coming up first by talking to you, by going like, "Hey, there's something going on." We do not have the luxury, like an automatic transmission, where we can look at a diagnostic trouble codes. We do not have that. The electronic sensors on a transmission are basically going to fall in line with the neutral safety switch, a reverse solenoid or reverse light switch, and possibly a skip shift solenoid. That's really it. Everything else is going to be all manually done. But we want to be able to try to determine whether or not the noise we're having from our transmission is from the engine, the clutch system, the transmission, or the diff. And to isolate that, we're looking at, what gear it happens in. Is it in neutral? What temperature it is? Is the vehicle at speed or is it idle? Is it going to be at a set RPM? Is it going to be during, half engagement or partial engagement of the clutch? We can look and we can have even a bad motor mount cause engine noise, not engine noise, cause transmission noise based off of the transmission might not be being lubricated correctly, depending on if it is shifted over one way or the other. Now, more often than not, our transmission noises are going to be affected by vehicle speed, and will be pretty non-existent at idle. If it's a situation that there is a noise at idle with the transmission out of gear or in neutral, then there is a possibility that it might not be the transmission that's making that noise. But we can see a bunch of different noises from a bunch of different type of components. A broken blocker ring, for instance, like what we have on the left of the screen, can make a grinding in gear and can also kind of make a fluttering type noise. To where broken teeth on the end of our speed gear there that's photoed on to the right, that can make more of a grind just when we're shifting into that gear. And then once it's in gear and locked together, it tends to not make any noise at that point anymore. Now, a grinding or a clashing noise caused by upshifts or downshifts is really common on manual transmissions, and is usually a cause of worn blocker rings. And the blocker rings are going to be our wear items inside of the transmission. So a typical transmission overhaul, you're really only just replacing that blocker ring, and that's it, along with the gaskets and seals and possibly bearings. But just these little blocker rings right here are the only items that are going to be worn out. However, these tend to prematurely wear out due to poor driving habits from the operator of the vehicle. Resting your hand on the shifter or not fully disengaging the clutch before shifting, not getting it straight into the gate, meaning that, if you're going from like second to third, you miss and you kind of go along the gate, that can cause damage to the blocker rings. And it will cause kind of a grind or like a noise from the transmission if you don't get it just right, but that will require you to tear down the transmission to see it. Again, we don't have diagnostic trouble codes, so seeing is believing. We actually do got to get the components apart to be able to see what's wrong. It also is going to be one of those things that we're going to be checking for when that noise happens. For instance, if the noise happens in every gear but fourth gear, then that tells you that it's probably our pocket bearing or that really important bearing that supports all three shafts of the transmission and can cause the transmission to grind itself to pieces. If it doesn't happen in fourth gear or whatever direct drive is, then that's going to be ruled out because we now have eliminated all the speed gears, all the counter shaft gears, and we've just locked the input shaft to the output shaft. So the only things inside the transmission that could be making noise would be the support bearings on the outside of the case, which is pretty unlikely, and those would be making noise in every gear at all times. Now, a hard shift is a different thing altogether. So I have a speed gear photoed here, and we've painted yellow the blocker ring teeth or the dog teeth that have been knocked off. Now, this will be where you're trying to shift and you can't get it, and it feels like the shifter is coming against a barrier. Now, this having some of the blocker rings still intact, you should be able to and then get it into gear eventually. But a hard shift concern meaning is exactly what it implies, that it is hard to shift it into gear. This can also be due to a binding or warped clutch disc, and we do need to try to find the root cause. Again, most of the causes that we're going to have in terms of transmission issues will be driver related. They will be related to how the operator was driving this vehicle. But either way, we're wanting to look and see if the engagement is tough and when it's tough. Now we can rule out the clutch, and the clutch being an issue is if we can bring the vehicle to a stop, we turn the engine off, if we can then get the transmission into gear easily. If we get the transmission into gear easily and then when we turn the engine on, it's difficult to get it into gear, that is an indication that we have a worn out clutch or there is a clutch issue that could be causing us to have a hard shift concern. Now, hard shift concerns can also be related to bent shift shafts or rods due to people again resting their hands on the shifter. Once you get it and shift it into gear, you take your hand off of it. You don't rest your hand on it the whole time. We can also have too where a clutch has had like a slightly leaking clutch actuation solenoid for our throwout bearing, and that has caused the gears to drag over time, and that over time will cause us to have an improperly shifting transmission and for it to wear out. We can also have worn or stuck detent mechanisms that will usually cause the transmission to kick out of gear, which again, as I brought up, when those detents fail and the shift knob hits you right in the hand, it's not always a nice feeling. And then it also too usually happens when you're in a forward gear and you're trying to take off and accelerate. So you can have it pop out of third gear, for instance, and then you have to really, kind of abruptly get it back into gear. Usually the telltale sign that you have a detent that's worn out is if it's popping out in gear. If you keep your hand on the shifter so that it's staying in gear, you'll feel for the shifter trying to push against your hand, and that's going to be something that does need to be checked again with an overhaul. Broken components can also cause the gear to snap out of gear or pop out of gear, or to not engage whatsoever. So, like what's photoed here is an example of a reverse idler slider, and it is broken, so you won't have reverse. Very common on transmissions because the reverse idler often is being shifted up into place. If we're not fully coming to a stop when shifting into reverse, we can very easily break that, and we can break that to where we have all forward gears, but we do not have our reverse gear. All of these different complaints, you're going to have to test drive the vehicle. As I brought up before, we don't have the luxury to be able to look at diagnostic trouble codes with manual transmissions to kind of get us in the realm of possibility. Instead, we're having to rely on a test drive, and we're having to go through and have an understanding of our expertise and the critical steps in which it takes to diagnose it. There are flowcharts that can walk you through it available from the manufacturer in the service manual, but we do want to make sure that we're paying attention to that. We're also wanting to look at TSBs and recalls because we do not have diagnostic trouble codes that we can fall in line to. Oftentimes, manufacturers, if there's a known issue with the manual transmission, they will post that on a technical service bulletin, and you will have the ability to then double check to see what's going on. Now, I brought up paddle shifting a couple slides back. Paddle shift transmissions will have an electronic shift mechanism. That electronic shift mechanism will use solenoids, and that will have diagnostic trouble codes, but that's only for the shifting portion of it. That's not for the actual gearbox portion of it. It will have its own computer, and it will have solenoids on the side of the transmission that will be computerized and controlled, and will be able to run its own diagnostics. You will have to have a specialized scan tool to be able to read these diagnostic codes. And quite often, if it's usually going to have an electronic shift set of shift solenoids, it's also going to have electronic clutch actuation or throw out. Now that covers chapter 12. When we get into chapter 13 and 14, we're going to talk about transaxles and the uniqueness with those type of gearboxes, as well as what it takes to start to overhaul a transmission, because we're beginning to do that in class. But I appreciate you sticking to the end of the lecture. Do keep in mind, I'm going to be testing you on a lot of stuff on the midterm and the final that will be only in the lecture and not necessarily be in the textbook. So you'll find that by reviewing this lecture content and video. So I do appreciate if you stuck around to the end. But thank you for watching, and I'll see you in the next one.